In this video, we're going to talk about the signals that are the most important for this course. Uh, we're going to see these signals over and over and over again. One you've already seen already is the sinusoid, and signals that are basically related to the sinusoid in some way. Well, then we'll talk about a very different class of signals. They're pulse-like signals. These you haven't seen in your calculus course. These are going to be interesting signals, as you'll see. But probably the most important thing in this video is the segment on how to think about signals, how to build them, and how to think about them as simpler parts. That's going to be a very, very important thing we're going to talk about. So, here's our sinusoid, and we've seen it before. As we've said, it has an amplitude A, which determines how big it is. So this negative part down here has a size of minus A, goes down to minus A. The frequency determines how often this reappears. This is a periodic signal, which means it repeats. And it's certainly clear that if you hop over to the next peak, you're going to get the same signal back again. Whatever occurred here is going to reoccur here, is going to reoccur here, etc. Well, the period we call capital T, and it's just a symbol that we'll use often for what the period of a signal is. How is it related to F naught? And if you think about it for a second, the sine wave repeats whenever F naught times T is an integer, which means that T has to be 1 over F0. So F0 again is the frequency in hertz, and this formula gives T in seconds. So hertz has units of inverse seconds, if you will. And then finally there's the phase, which basically defines how this starts at the origin. So that value right there is A sine of phi. So if phi is 0, this thing starts at 0 at the origin, and therefore there's no what's called phase offset. Now I should point out that if you have cosine 2 pi f naught t, it's another sinusoid, that's equal to a phase shifted sine wave. When it's shifted by 90 degrees, pi over 2. You should verify that formula is correct. I hope I didn't make an error, but I think it's right. And therefore a sine wave can be written in terms of a phase shifted cosine also. So there's really no difference between a cosine and a sine. They're phase shifted versions of each other. So this is what phase does. It moves things around in time. Now, the next signal we're going to talk about is the complex exponential. Yes, complex valued signals. So J here is the square root of minus 1. And this signal is incredibly important for us. It's incredibly important for all electrical engineers. This is another periodic signal. Its period is the same as the sinusoid we saw before, and its period is equal to 1 over f naught, 1 over the frequency. Now you can plot this in the complex plane. So this is the real part. This is the imaginary part. And it turns out that it goes around in a circle. So if you the angle at any one time is 2 pi f naught t, whatever time is. So as time increases, this angle increases, and this complex exponential looks like an arrow that goes around and around and around the unit circle, and the time it takes it to go around once is the period. That makes it periodic, and I think it's pretty clear, again, that that period has to be such that f naught times t is an integer. That makes the period 1 over f naught. Now, I hope you all know Euler's relationship, which says that a complex exponential actually consists of a cosine and a sine. So the cosine is the real part of the complex exponential, and the sine is the imaginary part of the complex exponential. I cannot stress how important these signals are in our course. So, in particular, the complex valued nature of it is very, very important to understand. So if you're a little unfamiliar with complex numbers, Euler's formula, I suggest you look at the complex numbers video, which I've made. I hope it will help you develop a better mathematical appreciation of complex numbers and complex valued signals. Okay, let's go on to our pulses. Pulses are going to be a little different than what you've seen in calculus courses, because most of them are discontinuous. You probably shied away from discontinuous functions in your calculus course, but pulse signals occur all the time. And perhaps the simplest signal is what we call the unit step. It's equal to 0 for t less than 0, and then it's equal to 1 for t greater than 0. So it looks like a step up, where it gets its name. Now you probably noticed right away I didn't define it at the origin, and that's just the way it is. Its value at the origin is undefined. Turns out it doesn't matter what its value at the origin is, and you may not like that, but get used to it. It turns out it's going to occur all the time, and it turns out we don't really care what the value is at the origin. It just plain doesn't matter. So, another signal that has discontinuities is what we call the unit pulse. And by the way, the word unit here refers to the fact that the amplitude of this pulse, the amount it jumps, the size of its discontinuity is 1. So the amplitude of this pulse is 1 because it's a unit pulse. So, as the formula says, it's 0 for t less than 0. It's then 1 in between 0 and delta is called the pulse width. And then it's 0 again afterwards. So it pops up, stays constant, then goes down and continues on. So that's a single pulse. We're going to discover that the pulse is used very frequently in digital communications. It's used to represent bits. That's what makes it extremely important. And the next signal we're going to talk about is the square wave. So a square wave is a periodic signal, has a period of capital T as I've labeled it here, because you can see it repeats every capital T. It goes on forever. The amplitude of a square wave is, there is no convention for that. We don't really talk about the unit square wave. You explicitly have to give the amplitude, which I've just labeled here as A. So it has discontinuities at the origin t over 2, t, 3t over 2. So it's discontinuous every t over 2. And what its value is at those points just plain doesn't matter. It's discontinuous. We'll just have to appreciate that as we go through the course. All right, here comes the good stuff. Here comes the part that's very, very important. We have to build signals. What do we mean by that?